let's get started. I have way too much that I've tried to pack into this, so I will be speeding along. But go ahead and ask questions. Also, I am easy to find if you have more to ask me about or want more description, background. It's like, absolutely find me. I'm presenting this in order to get feedback. Okay, algorithms for trees. Foldable, applicative, and traversable.
These are algorithms for trees to apply to the world, or us to apply to trees?
Sorry?
These are algorithms for trees to apply, or is it to apply to trees?
Well, we want to apply our algorithms to trees.
Okay.
And we want our trees to, we want all the trees that we have for the standard, I want the standard library to support them, at least as well as we have support for ranges, but I'll be getting to that. Background material on my slide, deck. I try to make presentation accessible, it's like, etc. So algorithms for trees. We got foldable, applicative, traversable. So functor patterns have proved widely useful. That's all the core map operations. Foldable is roughly what we get out of ranges. But there's more beyond that we'd like to use in a lot of contexts in C++. In particular, I'd like to use them for trees, but they apply, these patterns apply to lots of things. Now, one of the problems with using range algorithms, the structure of the thing that you're looking at, that you're applying the algorithm to, is important. Not everything can just be flattened out. You lose information. The other thing I'll be talking about a bit is monoids, not deeply, but monoids are something that have a way of creating one that's well known and a way of combining two of them. This surprisingly small amount of requirements actually gives you a lot of possibilities. And one of the things I'm aiming for, I'd like to get fingertree, which was invented 2006. So it definitely postdates almost everything else in the standard library by 10, 15 years, but is not exactly new at this point. Broadly adopted in other languages. The challenges were basically, it's a fairly functional programming data structure. C++ was unhappy doing some of the things that this data structure asked for. We pretty much fixed them, and you can pretty much now do a implementation from spec using C++ 23 and 26 tools. This is what I was saying. So trees carry shapes, and these are the abstractions we're going to be talking about. Let me keep that shape. I don't want, if I want to apply an algorithm to a tree and I want a tree out, I can't use like the range fold algorithm. That flattens everything. Maybe I could use some other tools to reassemble it into a tree, but that's just all wrong. You've got a tree in, you want a tree out. Foldable. Basically, we're going to have an opt-in hook. You're going to be we'll define a fold map, which is like, I've got a series of things. How do I combine them all together with the standard kind of like, in a list or a range, it's like putting your operation between every element in the range. We're going to do the same sort of thing with other kinds of data structures. Foldable is the flatten everything idea, though. And this decouples algorithms from the particular representation of your data. And we want to make these open also. one of the difficulties with a lot of things is like, oh, they didn't implement exactly the right interface. I've got no way to opt in from the outside. Ideally, you get them to do the opt-in, because same problem as with someone writes a operator angle for vector. Everyone wants to do it for their test cases, but if you leave it lying around in public, then you have two of them. At best, things work peculiarly. At worst, everything goes downhill. That's it. Yeah, and we don't need to flatten everything necessarily. So applicative, we've been talking about this for a few years. This work partly builds up on a talk that Bendine gave a few years ago about applicative, the forgotten type class, where he came through the insight that it's like all of the stuff that you see in other languages about partial application and currying and doing all of this stuff, that's actually implementation details. Conor McBride, who invented these, was trying to solve a particular problem and a repeated pattern that he was seeing, where he wanted to take a pure function and apply it to a bunch of arguments that were in some context, like being in a vector, or being in a SIMD vector, or being in a tree, and having each of those, and do the right thing for whatever that context is. Very useful. Really nothing to do with partial application or like binding elements or any of that. In fact, his original proposed notation was these really fat brackets with a function and a bunch of arguments. He also was proposing at the same time Traversable, which is a generalization of Foldable, but is not requiring you to flatten everything. Not everything that's foldable can be a traversable, but pretty much everything. It's like you have to hunt down the dark corners of things where it's like, oh, that this foldable isn't traversable. It's like, it's possible. There are examples. You almost never run into them. One of the nice things is so a tree stays a tree when you traverse and apply functions to your tree. You can also commute containers, the things that you're operating over. So you can turn your vector of SIMD vectors into a SIMD vector of vectors, or your vector of senders into a sender of vectors. Like, this is really powerful, just being able to swap those things. And it's like, in detail, figuring out how that works is kind of mind-bending, but like, it like just falls out of a few simple, fairly simple operations that you define. You don't have to work out how to do it. It's known from principles, provably, how this works, as long as something is a traversable and an applicative through the things you're running on. Let's see, so I'm going to be stopping short of monads. So this is not a monad talk, for a change. There is a monad for trees. It's weird. I've seen hypothetical uses for it. I'm not going to talk about it. The approach I'm talking about can be extended to monads, but like too much. All monads are also applicatives. There's a strict, like, you can get the applicative out of the monad by just like, oh, these are the correct definitions of it. There's actually 2 or 3 ways you could do it, but there's only one that really is the one you want. Not all applicatives are monads. In particular, what I'm going to be talking about is zip list, which is data parallel operations, which is SIMD. So that's an important case for us. We'd really like to be able to take all those pure functions that just take doubles and apply them to the bunch of SIMD things that we have in SIMD vectors and have it just do the right thing without having to write it every time. Okay, yeah, ranges flatten the world. Brilliant abstraction. This it's like equivalent to the list monad, generalizes everything. It's like wonderful abstraction, powerful in lots of cases, not always what you want. It's like it assumes that you can just turn things into a linear thing. It's fine to just say, I'm traversing my tree in depth first, and I get all of the elements out, and then I can put that in a vector, and that's all I'll need to do. Like, that's just not always the case. It's like, sometimes it's semantically neutral. Sometimes really all you want to do is just iterate all over everything. Ranges are great at that. It's like gives us lots of compositionality. It's like lots of power. But we want to go further, and we want to provide I want to provide these things in a generic way, in the same way that we've done for ranges, in the same way that the STL originally had containers and algorithms and iterators. It's like separating these concerns out makes it so much easier to compose everything later. Structure sometimes carries meaning, not just some organizational stuff. If you've got a balanced tree, that balance is an important property. Linearizing it, you don't have balance anymore, and trying to reconstruct that may not give you back what you started with. There can be more than one balanced tree for a particular sequence of data. It's like reconstructing it is like, well, first wasted work, but also just that's not where you were, and you don't want to do that. Yeah, and the same in-order sequence comes from many different trees. And if we flatten too early, we lose some leverage. We've lost some knowledge that we might be able to take advantage of. But basically, trees that are not sequences, like expression trees. That's your ASTs. It's like +2, 3, or +2, like times 6, 5. It's like that structure is important. The evaluation rules are important. Order of operation is important. Just traversing that and linearizing it, unless you've already set some rules like, oh, this is defined to be RPN, and it's like there's a unique way of doing this, you've lost important information. Syntax trees, similar. Measured trees, we're talking about these much more, but it's like you've got some measure that summarizes internal data of your tree. Like everything under this node is less than 6. So you can then search for things much more quickly. Okay, let's talk about visitors, pattern matching, and some missing syntax. Like this is unfortunate and why I'm a little bit salty about 26, because we did not get pattern matching, and it was visitors kind of manual recursion control. It's like you define your visitor, or like this standard visit operation for a variant or top. It's like if it's one of these, do this. If it's one of these, do this. If it's one of these, do this. They are pattern matching. Quite literally, the visitor pattern came out of the implementation of pattern matching in other languages, and this information was lost and then rediscovered by other people who were like, oh my God, there's pattern matching is like visitor. And it's like, yeah, that's where it was stolen from. Like, pattern matching is so much nicer to work with. So languages that have pattern matching will implement things with the visitor underneath that they construct for you out of the pattern matching that they're doing. So this was natural for some of the people in the pattern movement, like, oh yeah, I can apply this lots of places. It's a great pattern for languages that don't have pattern matching. I can do all the same things, and you keep going with that. Control flow is explicit, kind of noisy though. It's like there's a lot of noise in writing a visitor in C++, even if you use the standard overload trick. I think
I wish it was standard.
I want to standardize it at this point. It's like, yeah, so it's only 6 lines of code, but why should everyone have to write that?
And by right, you mean copy from Stack Overflow
Yeah.
like everyone else. Or...
Yep. It's like, I'd really like to express these in terms of pattern, what the APIs in terms of pattern matching. I can't because I can't prove that we've got it yet. So, best case, we get both at the same time, and people are confused as why there's any of this visitor stuff visible. Kind of like how we ended up with std-bind and lambda arriving at the same time, and when you actually have lambdas, there's no reason at all to use std-bind. The good thing was, though, at the time, I got std-bind like 5 or 6 years before I got a compiler that could do lambdas. So, you know, there's history in my code base where it's like, yeah, if you ever touch this file again, just replace this. It's like, and I come back years later and no one's touched it yet, but it's like, not really hurting anyone. It's just a little more expensive to compile. So what I'm overall going to be proposing is a implementation of type classes brought over to C++, kind of based on the concept mapped ideas. This is also an internal implementation technique that GHC uses for doing type classes. Well, I'll get to that. But type class style APIs break apart the concerns. You get a separation of concerns. So it's like, I have something that I want you to operate on. I want you to use this kind of applicative, which implies a bunch of verbs, not just one, but like they come in a set. And I want you to work with this way. There are times when we can probably guess which one you mean. Sometimes it's flat out impossible. How many monoids could there be on int? Like plus, times, min, max. Like there are others. There's no good choice. We shouldn't give you one. It's like we have to ask. For others, there's a very good chance we can guess. But in case we're wrong, we want to provide a way for you to say, use this one. Or if you've been given one, you should be handing it on if you need to anyone so they don't get a different one to use when they try to figure it out. Designing for today for tomorrow's syntax. It's always predicting the future is always a little hard. I really have confidence that the current pattern matching proposal is sound. It's like all the edge cases have been worked through, but it keeps requiring convincing everyone from scratch each time. It's like, or someone wasn't there before. So it's like, what about these cases? What about these cases? What about these cases? And it's like, oh, yes, that's a good question. This is how we handle this case. This is how we've handled this case. I know the problem you're trying to get at over here, but that's strictly worse if we do it. We'll see. So, okay, recursion schemes you can actually use. If we're talking about trees, we're talking about recursive data types. It's like, how do we recurse down them? Biggest problem in C++ is you can't actually put an element of your thing inside you can't put a struct node inside your node struct. You need to indirect somehow. Like other languages get this for free because everything's boxed and indirected. We now have an indirect in the standard, which is a very good box. Or you can use a shared pointer or something, but you've got to deal with this somehow, the structural recursion of this. And you don't want to actually write these all the time either, because the patterns of recursion are generic. What you want to do at each of those is different. So F-algebras, functor algebras, big fancy word. All it really means is here's how to evaluate when you hit one of the things that might be in my tree. You might have different kinds of nodes, for example, or for an expression tree, you want to distinguish between plus and a constant and multiply. So the F-algebra is just like the algebra of what do I do when I hit each one of these? Now the interesting thing is, it turns out this is really all you need to define in order to apply and evaluate your tree or your recursive types. So it's like we separate out the recursion strategy from the business logic that you're applying to it. So you could use the same recursion strategy to have your pretty printer and your expression evaluator. Like, catamorphism, real fancy word. It looks like the guy who's written most of the libraries that do this has decided that catamorphism really is just too confusing. I can't remember what he calls it now, but it's like it's something that's looked a little bit more intuitive. But basically, catamorphism is just general fold. Like, instead of just the one kind of thing, handle all the kinds of things that might be in my expression tree. And then we can hand kata, which then just recurses down the tree. It's like, what do I do? Oh, that went off the edge, sorry. But it's like, yeah, it's like, so if I have a expr a constant, we just return the value of it. If I've got an expr add, we return the a plus b value. If we've got an expr or mul, we return the a times b.
Just select the text.
Hmm?
Select the text, it'll show up.
Ah, good idea. Well, okay, but I have to be over here.
There we go.
Yeah, it's like not trying to hide anything off the slide. This really is boring code. It's like it's Ronseal algorithm. It's like Ronseal is it is what it says on the tin. It's like, but given this is enough to evaluate a tree. And it's like we can hand it to a lot of different things that do these evaluations, and it just walks down and says, oh, this, that. I like roll up, here's the answer. It's like this sort of thing, fairly straightforward to standardize. We probably should have this. Yes?
So with like expr add or expr mul here, unless none of these types unless add and mul aren't recursive, and they just actually have a double left and a double right, where does like the recursive step go? Where if you had a tree that's like add of mul a constant, b constant.
It rolls up from the bottom. So what you're really evaluating is the expression that was on the right.
Right.
It's like, if you're a multiply node, you're going to multiply by whatever the evaluation of the right-hand side was. It doesn't have to be a constant. It could be, it's like, kata, the recursion strategy, takes care of that for you. All you need to do is, what do I need to concretely deal with? The things that I don't know how to deal with get deferred. And it's like we're going to be getting a result of a double, because this is really simple. It's like all you have to deal with is a double coming in, because that'll be the result of the evaluation of the tree under you. assuming it was not broken, like you just have something meaningless down there, in which case evaluation fails. So,
How do we combine the results of eval algebra in this case?
well, at each level, like if you've got
I'm just missing where that definition is.
yeah, well, the evaluation rolls up.
Yeah, sure,
So-
but you're returning doubles, and I don't see where those get passed into the.
Well, the thing is, you don't need to. It's like all you need to be able to do is handle each kind of node, and the algorithm that's doing the evaluation and roll-up handles, like, I'm not going to hand you a tree I'm going to evaluate the tree that's below you on one side. That'll have one evaluator be a double, and that's the right-hand side of your multiplication. Similarly on the left. Yeah.
So can you describe exactly what the types coming into this originally are? Is it some kind, like an expression template like tree, or is it a dynamic?
Nope, it's like nothing very special about this. This happens to be pulled from a fixed point tree, but it's like could be a binary tree, could be anything. It's like you need to define the rules of how to recurse down the tree.
Okay.
But that's generic for the tree as opposed to what you're doing with the evaluations. It might be a little clearer. It's like, yeah, so we're separating recursion from the business logic. Actually, I'll hold that. There's going to be some more about trees, and we'll see these exact trees a little bit later. That's it. Okay, type class object pattern. This is core fence posts that I'm working on. This is a generalization of customization point objects. A CPO just has an operator call. These have named operations, and the names are the generic names of the algorithm of the type class. So let's see, it's like type class lookup. There's one object per concept. Well, logically, one object per concept in the context of that particular thing. But we can use variable templates to look it up by type, or just supply one or construct it however we want to. As long as you meet the contract of this has the 5, 7, whatever number of methods on it with the right shape, consumers of it do not care about the implementation. We care about the implementation, or I care about it because I don't want to hurt you in trying to provide these for your data types. But we can look up the object in various ways. So there'll be a foldable type class on T, applicative type class on T, traversable type class on T. Those are all variable templates that, it's like there's an object at the other side for all the reasons that we like objects to avoid ADL and all of those things, as well as being able to then pass them forward. They might be all full of just static methods. There's no state that we're interested in. But there could be, if you were trying to debug what's going on with your thing, you could record some trace, do anything that you need to or want to. Types can opt in by specializing the variable template. Hopefully you do that close to each other so you don't run into the problem of 4 people in your department all trying to provide it slightly differently. For someone else's type over there who's not wanting to cooperate. But you can retrofit things that are just not in your control coming from some entire third party. So it's an open extension form. There are 3 lookup modes that are built in. It's like we could just look up the exact one that we're trying to find. We could be passed one explicitly. We can use a non-type template parameter. which is now called what?
A constant template parameter.
Yeah,
Because
it's
you're
like,
passing a constant.
yeah,
We have
I know.
concept. We have concept and variable template parameters now. They're all non-type.
I know. It's like, but yeah. So a constant parameter that it then can give it a name, be defaulted, and it's available inside the function or the your class. All three end up with the same dispatch mechanism. There's a function and name that the compiler can see and maybe even see through and optimize for. Yeah.
Is this advice of you providing the definition close to use not an ODR trap? Because you're going to have the same symbol.
No, it should be close to the definition of the type.
Oh, okay.
Yeah,
Yes.
it's like
No.
not close to doing it at the usage site is a fallback. I don't have a choice
Right.
mechanism.
Okay.
It's like, yeah, it's like, no, you really want them to provide these traits and type class objects. They may not have existed when the thing that you're working with happened. So this is how you can look them up with a constant template parameter. Not terribly surprising. You could write this in code inside the function. It's like, this makes it a little bit easier on the caller because then they don't have to do this, and it just works in the normal case. Unfortunately, because it is dependent, it would have been nicer if we could have put it in the front, but you can't deduce things that way easily, or I couldn't figure out a way of doing it. So if you want to use this form, you need to provide like the template signature, or provide a alternate form of the function that just takes one of these, like as the first parameter. When you're implementing these, there's usually, for some, you're going to have to implement all of the functions yourself, because like they're all independent and that's just how things work. Monoid, there's really no way to get much of the rest of Monoid out of any part of it. On the other hand, for things like Monad and Applicative and Traversable, there's really only 2 or 3 functions, usually 2, maybe out of 3, that you need to define, and everything else in the interface is defined in terms of those. Now, you may discover that that's not the most efficient way of doing something for a particular type, so you can provide more if you want to. But very often the base definitions are quite good enough for almost all purposes. You need to have something a little pathological for them to really not work. Okay. Yeah, you might be leaving some performance on the table. Like that's future work and not barred by any of this at all. So each wrapper has a CRTP base and uses deducing this to reach it. And then we can also have using declarations to break the loop that we'd otherwise fall into, which also uses deducing this as it ends up to say that, okay, yeah, there were 3 functions all implemented in terms of each other. The compiler will just yell at you for that. So you provide a using declaration that's like, yeah, my implementation one that's the basic, that's the applicative is wrapped in as the template is the real implementation that should be deferred to, and then it all works. The compiler is then happy. I would have been happier if didn't have to do that dance, but It's like this at least provides the hooks and doesn't lock you into, oh, you have, it's like for monad, which I'm not really talking about, but like sometimes join is really easy to implement. Sometimes bind is really easy to implement. You can do things in terms of either, but one is easier to work with for your type than the other, and you would rather do that and not have to figure out how to do the weird thing and provide that. You just get to provide the ones that you need. Dispatch still fully static. There's no virtual dispatch here. Transparent to the compiler. Compiler can, it's like just see all of these things and do the direct call or inline it or whatever. It's like from a compilation point of view, this is not type erasure that's hiding things from the compiler. Just like we have in ranges. It's like there may be times when you do need to do some type erasure, but it's like mostly have avoided that. Okay, so functor, the very foundation thing, all of these things are functors. Functors are things that have values inside them that you can apply functions to. You might not be able to actually do anything else other than that, like not even get them out again. Those are like the weird edge cases. Most things let you get the values back out. You might not be able to construct something from scratch. Like the functor like doesn't know enough to say, oh yeah, there's a 0 value. It's like no, you've got to give me the container to operate on before I can do anything. Minimal hook, fmap, which has some weird historical naming weirdness. And then you also get replace, which is like basically whatever's in there, this value, put it there. It's like, it's a nice basis operation. You wouldn't think of it until you could do this with fmap, and it's really done with, can be really done with fmap, but it's like, comes up often enough that it's like, oh, we can give this to you basically for free. Can look up the functor type class on std optional int, because optional's a maybe type, and a functor. It's like, you can apply functions to the value in the optional. If there's nothing there, it does nothing. If there's something there, it calls the function with that value and then returns a optional with that value in it or empty. Derived replace. It's like, here's how we use fmap to stick a value in of this. It's like, this is not supposed to be terribly interesting code, but it's like, oh yeah, you can do lots of things with the generic operations. I've also got tests covering that. It's like there's a law that a functor that if the function that you give it is the identity function, that should do nothing. That sounds really obvious, but like this is one of those things that you can inspect, but it's like you either have to write tests to check that it's working or white box inspect the code. Once you know that this rule exists, you can reason about lots of other things that these do. And it's like, so we check a few of these to make sure that that the implementation isn't just totally broken. Let's move on up the stack a bit. Traversable inference, preserving shape. Foldable versus traversable. Foldable is doing things over a sequence. Traversable is doing the same thing, but taking into account the shape and context inside that shape. Foldable is summarizing a sequence, essentially. One of the ways you can summarize a sequence is producing a sequence that comes out of it. But usually you're doing some kind of reduction operation. It's like traversable preserves any effects in the structure that you're mapping into. And this effect might just be the parent-child relationships in your nodes, or it might be more interesting effects, like senders getting ready to being able to send a value later. Yeah, for trees, it's just like the difference between counting all the nodes, which you can do just with a fold, with relabeling them somehow and getting a tree back out that has different information. You can't do that with a range or a fold. You've strictly lost some information. Yeah, and the contrast is like it's either flattening or preserving the shape. So foldables are things that are just like not strictly true, but in general, it's like there's a nice two sequence or two range operator for your type, and that's how you do all the fold and gives you access to all of ranges. It's like traversable can do more because you can keep your original branching shape. You have context that's applied to you when you're doing the work. So some simple examples like I can traverse the optional double and I still get the optional out, or I can do this with a tree and get the tree back out. So got three kinds of trees here. Actually, well, no, I've got 4 kinds of trees now. There's a typo here. Okay, got a fixed point tree, which I'll talk about in a minute, shared pointer binary tree, the kind of thing that you'd write for yourself all the time, fringe tree, which is like a simplified finger tree, and then finger tree itself, which is the really complicated one. It's like, call looks pretty much the same for all of these, but what I've done is provided the type class adapter that's special for how this particular type works. But given that, I can do foldable length and get the length out for all of these, or traverse them. So let's talk a little bit about foldable. Monoid is what glues folds together. Your monoidal operation is what goes between each of the things that you're folding over. And it's got something on the left and something on the right, and it combines them in some ways. It's like, turns out there are a lot of useful monoids, very few properties that you need for them, but it gives just enough to do a lot of reasoning about the kinds of things. Just the fact that you have a binary operation that takes a type A and a type A and results in a type A is a lot of information. It turns out. It's like, this seems not very much. But we rely on it. We rely on it to do arithmetic, basically. Okay, so one hook, it's like everything else can be derived from fold map, which is the sort of the fused operation of map and fold. It's like, I've got a function I want to apply, and I want you to accumulate fold, reduce all of the results of that function. It's like, from that, well, you can do one or the other by saying, oh, one of those was an identity no-op. You could write them both, maybe get a little bit more out of it. Honestly, the compiler sees that this is trivial and just ignores it, so, if it can. All you need to do is implement fold map for your type. Everything else in foldable comes for free. It's like the only real rule is that whatever traversal order you're using for your type, you have to always use it for anything that you're implemented, or you'll get different answers out in ways that could actually hurt you, because let's say you've got minus as your operation that you're doing. Going from the back to the front versus front to the back just gives you a different answer. And if the rest of the code is assuming that those are going to be the same answer, now you're in a state where your program is confused and lost. And that's not a nice thing to do to it.
Didn't you choose monoids because you wanted the associative law that would rule out minus?
Yes, it's like when we're strictly treating it as a monoid, yes, we get to rule those out, which is why there's monoid constraints on some of these. Fold doesn't necessarily enforce monoid.
Of course.
Right. Okay, and some tests as examples. Applicative, next level up. Basically, pure functions over effectful arguments. Like you want to apply your add function to your pair of SIMD vectors of double and have it do the right thing. This is not how ranges work, although ranges, we have some zip functions. When you're doing combinations of this, like this with ranges, you get Cartesian products of the two ranges. The SIMD thing is usually, when we're talking in this context, zip list, because you're zipping things together. When you bring something into your pure function or pure value into a zip list, it's repeated infinitely, or really as needed, or not really copied at all. But this lets you zip that function together in parallel with however short your shortest SIMD list is. And my insight a couple of months ago, reading these papers, is logically the interface that you want is something that looks like invoke, not something that looks like Haskell, or like with partial applications that you're accumulating somehow, and like, where do I ever get partially applied functions other than senders now that I work with? I've got a bunch of things. I just want to apply this function to all of these things the right way. Invoke lets us do this. Inside the implementation, we need that partial application stuff because that's how they fit together. On the user side, you really don't care about that most of the time. You could get at it, but it's like applicative is a strict generalization of monad. Any monad's an applicative. Not all applicatives are monads. Zip list, SIMD is not monadic. It's like, so there are more of them because they're weaker in strength. They let you do less things. They let us do a lot of things we want, though. Okay, so use case. I want to, like, applicative invoke. It's like this function that takes 3 values on my, I didn't even show what those were, but it's like I've got a vector of AX, AY, and AZ that are, and vectors applicative because it's a monad and like because ranges are monads. But then we're just going to apply all of these the way, whatever way is appropriate for the type of those A's. It's like if there's SIMD lists, we just zip down them. If they're ranges, we're going to take the Cartesian product of all of those ranges and add up every combination and get the value out. If they're senders, it gets stranger what they do. But it's like, if anyone tells you that knowing that something is a monad or an applicative tells them what it does, they're probably lying, or they're one of like 3 people in the world. You know the kinds of things that you can absolutely do. You have to work out in context what sorts of things they do. I'm not going to be surprised by anything that SIMD does, that a SIMD vector does with this. Some other thing, I got to work out what it means in that context. It's like this tested. It's like We can do short circuiting with applicatives like we could in other contexts. Like if you know you're not going to make any progress, you can then quickly get out and bail. Like optionals are good for this. It's like we can, this is some implementation details, terminating partial application. There's a trick that Ben worked out a couple of years ago for figuring out when you'd gotten to the end of your partial application of the functions, and actually then just that's the value. Don't try and add anything more to it. Won't show all that code. There are some laws about this, about how they can be interchanged. This is important primarily that it proves that the form where it's just a pure function followed by all the applicatives, any expression involving applicatives can be converted to that form, so you're not losing anything by basically always using the natural form. Let's go over to traversable, which and applicable and traversable go together. They were proposed at the same time, same paper. Traversable uses applicatives to do its job. So it's like, yeah, commuting shape and effect. It's like it's got pretty much all the same operations as foldable, but it's structure aware. We can model success. I think I'm a little ahead. So yeah, we can model success for this, checking if something has a value, using optional as a traversable. It's like failures propagate through in ways that you'd like. Sequence is an interesting API. It helps commute containers around. Sequence is one of the, like how you get that vector of SIMD into a SIMD of vector, or vice versa, depending on what you're trying to move on to. Machinery gives this to you. It's like, well, you have to write either traverse or sequence, but one of them will generally be very easy and natural to write, and the other one, you would have to follow its definition and implement it, but you don't have to. I'm running tests to make sure I'm not lying to myself. After all, it's like Feynman rule. I am the easiest person to fool when I'm trying to do my own work. Tests keep me honest. It's like tests fail. Okay, I stop. I should. It's like. When I'm implementing something new, my first test when I write it fails. This tells me that I've at least wired it incorrectly. It's like, because I have made that mistake. It's like, how is this possibly working? Okay, it's not even C++ anymore. How is this actually possibly working? Oh, it's not compiling at all. That's it. It's easy to miss that you only have 302 tests, than not 303. Yeah, there are some laws about how traversables have to compose with each other. We can't prove them for your code. You're obligated to do this proof. It's usually pretty trivial. But if you lie about it, well, the code might still compile and your program might work, but you're leaving an unexploded landmine for someone else later who will try and rely on some property that you didn't need. Basically that, if you've got a function that converts between applicatives, respects pure, traversal commutes through it. So you can do the inversion of things. And we can apply our functions like before or after. Right? So here, range and zip list, where zip list is our SIMD analog. I didn't have a SIMD implementation at hand when I was playing with this, so I just have a zip list. But I do have real ranges. It's like, and, oh, the codes run off, sorry. So yeah, I can, here I can take my range of zip lists and convert it into a zip list of ranges. It's like, or I can go the other way. I got a zip list of vectors and get that into a vector of zip lists. It's like, this is like matrix transposition you want to do. These are really useful and really painful to write on your own from scratch. And you so often have things that are almost in the shape that you want. This lets you get them into that shape. I haven't gotten it working yet because too many moving parts. But a big one is where I've got a range of senders and I want to turn that into a sender that sends a range. It's like, this machinery just does that for you. And you stick it in and it like all works. I've used it in other context. I just don't have it to show you. But it's like small matter of programming. But this comes up all the time where you've got, I've got these two containers in the wrong order in this thing. I have the vector of zip lists, and really I don't want that. I want it the other way around, because I want to hand off like like all of these SIMDs put together into one thing that then operates on them in a range-like manner, rather than trying to traverse them individually. So it's like laws keep us honest. These are the laws that let us reason about the programs. More importantly, they let the people who are writing the algorithms reason about what the algorithms that they're writing do. So you don't have to quite so much, as long as you pinky swear by providing a applicative or a traversable instance for your type that it behaves sensibly. Right. Okay, monoids and measured trees. Okay, monoid interface. There's an identity element for the operation that we're working on. And there's combine. It's like, these have lots of different names in different literatures. I picked these two because empty really did not resonate with me for most of the contexts that I'm using this in. And op is just too short to be meaningful. But on the other hand, one of the nice things about this type class, these names we only have to bike shed once. And they don't really matter. They don't have to be great names. Algorithm implementers will work with whatever these names are. What this means, though, we can use good domain-specific names inside the type, even if the operations are just strict mapping. Like, if you're just saying that it's like combine equals add, and that's all you had to do, it's like, fine, don't care, compiler's happy now. But that's a good name in context. We have so many arguments right now about like, well, we have like 3 different ways of naming a monadic join or bind operation across various types in the standard. And it's like, yeah, because bind and join are terrible names. Those are not the names that you should get. Okay, I'm not going to try and argue for transform as a good name for map, but that's a historic legacy thing. That was the name it was given 40 years ago. It's like, without even really considering what it was really doing. It's like, map's a nice name. Fmap is actually to disambiguate it from the original map in Haskell, which operated on lists, and they didn't want to change it because there were ways of getting very scary error messages out of the Haskell compiler, and they really didn't want to frighten their undergrad students. Haskell was a teaching tool. So Fmap, and you're not going to learn about Fmap for another 2 months. So it's like, and then why Fmap? And it's like, well, we needed a name. It's like,
I have a quick question about
yeah.
the last slide there, right? So you've been talking about like SIMD, you've been talking about doubles, these are all things I love, and then I'm seeing associativity and combine of A, B, and C, and combine of A and combine of B, C. And then you've also said like add. Combine could be add, and like all those things don't actually agree, you know, as
Okay, that's like,
associativity. Is this something that's really important?
well, adds associative. Well, okay,
No,
let's,
that's what I mean. Yeah,
yeah,
that's why I
let's
think those exact examples. Yeah.
right, it's like but you have to make that promise.
Right.
It's like, if you said combine with subtract, it will probably compile. It will not give you sensible answers. You may think it's giving you sensible answers. Igor, I don't know if he's here, but he had a talk where it's like showing that they had an algorithmic bug that lasted for years. They were trying to levelize a tree that was not a tree. It was a graph with cycles, and
it worked most of the time, so yeah, right.
yeah, it's like, and the things that came out looked sensible, and you didn't notice until something downstream broke. It was like impossible situation from this, and it's like, if you lie about the contracts that you're claiming to satisfy, all bets off. So yeah, it's like, you're promising these operations behave this way when you say, this is the monoid I'm working with. Implementing monoid works pretty much the same way. You have to say, it's like, this is my count monoid. It's got the identity, which just returns count 0. It's like, and the combine operation is just adding the left and right value that the count's holding. It's like, some generic helpers, like letting us get things in and out of here. Some tests to double check that not lying to myself. Associativity is what gives us some leverage here. And this is what Lisa correctly called me out on. It's like the associativity is part of what gives us this power. That it's like we can look to the left and look to the right and know that we're not, it doesn't matter too much that it's like which we're doing first or second. So we can regroup, do things, merge things in ways that are convenient to us and get the same answer out, setting aside things like overflow, underflow, nans, infs, like all the things that break everything all the time anyway. It's like, not promising magic, just.
Yes, I think what he was pointing out is maybe setting aside the fact that floating point addition isn't actually associative, it's just kind of close.
It's close enough.
It's close enough for government work.
Absolutely, government relies on this.
So saturating arithmetic, integer arithmetic is non-associative and can have arbitrarily large errors as a result.
Yeah, it's like don't go near the edges. I know that zero's an edge, so it's kind of a problem, but it's like,
I'm okay with this.
Yeah,
like,
it's
there's no problem. But
yeah, it's like
The integer errors
there,
by int max.
you're not going. I can't solve this problem. I mean, it's like none of us really can. We're kind of stuck with sort of. It's like how we're modeling the natural numbers with computers with finite space. It's like we're doing the best we can. It's like,
I mean, this had a practical effect on the design of the linear algebra library for us.
yes, yeah.
We had to decide if we were going to try to encode, define constraints on functions asserting that numbers were associative, and we decided not to do that because 2006 reflect reality.
Yeah, it's like, yeah, that's why I'm saying some of this is just pinky swear.
Yeah.
In the sense that it's like the algorithms may rely on this. You're promising that the data that you're feeding to it is not going to be such that it makes a difference for you. It's like, best we can do. For lots and lots of practical applications, that is completely sufficient. Yeah, so measured trees exploit this, where a measured tree summarizes the data in the subtrees that it's got. And this gives us a bridge from the algebra of what to do for particular kind of elements in the tree to aggregate some data up. So we can apply annotations to the nodes in our tree that summarize the information that's below them in the tree. It's like, so we can, depending on what we're trying to model with the tree, we use different measured things, but it might be the size of the tree, priority for measuring priority queues. We're using min or max as part of our monoid. We can do interval trees, which give the measure accumulates what's the total interval under me, and it's like you can nest things and overlap things in interesting ways. Cost measurements, on and on and on. It's like, now updating the structure means you have to, it's like any update has to update its summary, but that's only a small part of the tree. Like, it's only going to affect upward, and most trees are not very deep. Even large trees are just not very deep, unless you're deliberately constructing your tree that's made all out of left, and now you've just got a linked list. It's like, but try not to do that. Most good trees will help you with balancing, help you with this sort of operation, and all of those operations are still local operations that are fairly inexpensive for keeping the tree in the shape it's supposed to be. So we can do search and split driven by these measures. So I could say, okay, find me where in the tree this measure is, and you can pull it back out. It's just a simple search. Or split the tree. It's like, I want everything, I want two trees to come out of this split, one with everything to the left of this measure and one to everything to the right of this measure, deciding which one the middle goes with. But it's like, so it's like, you can it's like do these splits in O log n time, because it's like all you have to do is find the right point, and then this search is fairly straightforward because you're guided by the measures that are already in the tree. And then there's a split at index for index trees, which is like the notional count, notional square bracket index for what you're representing. Some of this falls out when you're using trees as indexes. A lot of times your actual data is over there, and you've got a bunch of different indexes all referring to that data over there. So you want, it's like, I want to search by this index. It's like, okay, this is cheap this way, and I just modify the index. I don't necessarily have to modify all that data or reorder it. Databases, like, you don't want to have to actually sort the database table. It's like, you want to take the index that's already ordered and just run through that. Okay, so finger trees. It's like, persistent data structure. This would be our first persistent data structure in the standard, where persistent means that the operations on a finger tree return a new finger tree, leaving the old one unchanged. It's like, lots of times you really just want to throw the old one away. That's fine, that's cheap. Still, it's like you're not paying a huge extra cost for this. There's tons of reuse in this data structure. It's been hammered to death for 20 years of implementation in other languages, filing off all of the little bits and pieces. So yes, it's going to, if you use it as index lookup, more expensive than vector, not that expensive though. O log n is not a really big number. It's like, yeah, it's bigger than 1. So cost-benefit trade-offs. Lots of times you really can't afford this. It's like, especially if you're using it for, like as I said, where, oh, I'm actually providing an index lookup into that vector over there, and the data in this tree are pointers or iterators into that vector or map that is not changing. So I've got multi-way lookup into that vector that I can keep cheap. And the API composes naturally with foldable and traversable because it's a tree. It's like you change the monoid that you're using for it, you change how the tree works. So we can provide on top of the base finger tree, we can get sequence, priority queues, rope, which is actually how I came into this because I'm been working with the text study group for 5 or 6 years now. I made the mistake of signing up. I'm now chair of WG16 Unicode study group. A core problem with Unicode text algorithms, they spend lots of time inserting and deleting one character at a time in the middle of the string to renormalize the bit that you just inserted. Like, oh, I have to fix up all the diacritics on each side of this to now follow all the rules, and the other side. And now you want to insert one more character in the middle of the string, or another string, or edit it in some way. I have to do it again. This is essentially a worst case operation for vector. It's why your editor doesn't have vector as the underlying storage for your edit buffer. There are a few classic ones it uses. There are ropes from the mid-90s, gap buffers where it's like there's two sides and some space in the middle to work. Since mid-2000s, a lot of other languages are using finger trees for this kind of operation. It's like trade-offs again. It's like you get good enough lookup in them. You get very good linear traversal through them. So if you're just running through the whole thing to like dump it into the vector or dump it to the text buffer, like that's linear in the size of the finger tree. Well, it's actually log n, but it's like these things are cheap enough. It's like so. Why do I want this all in C++, modern C++? Traversable's a nice abstraction, and we can retrofit everything to it. This goes together with the realization that the external iteration patterns that we have from classic STL with iterators that you work with that you then pass around is not as good a model as internal iteration. It strictly means linearizing things and has its own set of problems. It turns out to be much more effective to say, here, this is a thing that I want you to do with all the stuff that's inside you. You know how to do that. Please do it. External iteration, you have much more worries about, like, is this iterator still good? Can I hold on to it? When am I allowed to hold on to it? Is what I'm working on going to invalidate the iterator that I've got right now? It's like, and then you go look up on Stack Overflow or CPP reference to figure out, like, what are the iterator stability guarantees that this container gives me, and like, can I hold on to the iterator for the map indefinitely? It's like, that you can, and it's useful. Well, except for a few things, and it's like, am I ever doing those things? And it's like, getting out of that business makes your life simpler. So it's like rope priority queue sequence. They have traversable. They have slightly different traversable interfaces because they maintain slightly different invariants. Under the covers, it all goes down to the same code. It's like we can do this as a library today. It clearly maps well to pattern matching, which means we could get rid of some of the machinery. Any place that I've had to expose variant, which you unfortunately do, and I wish I didn't, because visit on variant is unpleasant. There are some ways we can make it better. I think standardizing the overload that we all write, like with one of the current really good ones that like checks that you haven't left something off, for example. Has a catch-all that says undefined. Because I have made that mistake and caused real production problems where it's like, oh yeah, they added a new choice in this set of operations coming in over the wire. Didn't exist at the time, so my switch statement just falls off the end. It's like, or maybe I was lucky and it didn't fall off the end, but it just logged something. But still didn't do anything reasonable. Hopefully someone gets told about it and we fix it, but being able to type check these things is so much better. Just a whole class of mistakes you don't make. Aside from Traversable, core API for trees roughly corresponds to what the core API in a container would look like. It's like, so standard, like you want empty, size, front, pushback, begin. You want this, I have two trees, the simple one that doesn't do anything fancy but is not very performant, fingertree, which is very fancy. Both of these, it was straightforward to produce these APIs. Yeah, you want to be able to construct them. You want to be able to deconstruct them. You want to be able to look at them from the left, look at them from the right, split them. It's like bulk traversal. It's like sort of your core operations. It's like create an empty tree, create a single element tree that's just lifting a pure value into your tree kind. Build them up from a vector, range, whatever. It's like by whatever rules you're saying, but certainly when you're trying to like cruft together some test data, this is easier than having the long boilerplate of left, right 7, right 6, left, and it's like assembling it all up from parts. Measure aggregates it up. Breadth, because these trees, the interiors don't hold data. All the data is at the edge. The use case I was talking about, like where there's a flat vector. well supports that. So what's the breadth of the tree at the bottom? You want to know that. And it's like, look at the leftmost, look at the rightmost. It's like head, last, tail. The tail dropped the element and like give me the tree and the element that was at the tail. In it, the other side of that. Cons and SNOC, yeah, we can bike shed. Don't worry. But it's like, but yeah, it's like these are historic names. Cons came from constructing a list, and you have a cons cell. SNOC is cons backwards. So it's like, oh, we've got a list, only the first thing is the list and the last thing is the element that you can get at easily. It's like someone was amusing themselves naming these. But as I said, we only have to bike shed once. It's like flatten, that's 2 range or 2 vector. It's like for each. Just the straight for each algorithm. Do something for each of the elements in the no allocation, no new tree. Just do something, and hopefully you're okay with. You didn't want to map. You just like wanted to print or like something for every element. It's like traversable. The whole interface fills a bunch of gaps with things you want to do. The interface is deliberately not as fat as container or string. It's like trying to hold it to a reasonable set that we can guarantee. And then traversable provides a lot of other things on top of that that allows more broad composition. For things that don't necessarily have the exact tree interface that I was proposing.
So Steve, about for each and for algorithms in general, does it still make sense to have parallel overloads of those?
Maybe.
Would it mean the same thing as it does for the?
Yeah, it's like that's entirely reasonable. I don't do those enough, so I don't think of them. But yeah, it's like entirely reasonable to have the parallel discriminator that is like overloads for that, so that you could, for each, all of them. Like, okay, yeah, write them all out at once and like make a mess of your console. But what is it?
Does par unseek make sense? Like does the unsequenced execution policy make sense if I can only?
I haven't done enough research in this space. Okay. It's like if it makes sense, it's well known, just not in the literature that I usually read. It's like none of this stuff is novel in any sense. This is like 20 to 30-year-old algorithm research stuff. So like if there are parallel versions of these, people have worked on them.
So you're asking specifically about for each?
Yeah, or generally these tree algorithms, right?
I mean, for each par and seek, I think works.
Yeah, I mean, it depends on what you're doing. But
well,
I mean,
but that's in some ways, if it's inappropriate, that's a you problem.
Yeah.
It's like, It's like, if you're for each, whatever that function does is all independent, and for each is not a map. You're not modifying data. You're just running a pure function that that has no side effects on the tree. It could do whatever it wants because it's like, oh, you could be passing a closure that accumulates data or whatever. That's its business. But if there are a bunch of independent operations, I don't see why they couldn't be done in parallel. But it's just not my everyday research, everyday job, so I don't tend to think of those. Okay, so just because it's like names I'm proposing, names in other ecosystems that have these same ideas. What names am I stealing? Like sometimes none, sometimes they're the same. I did not spend a huge amount of time on this. Having been through LEWG enough times, I don't want emotional investment. So it's like, all of these have fairly standard names in literature. Every bit of literature has slightly different names, of course, but it's like applicative. Similarly, we've got things. Because operator overloading is so fraught in C++, I've just given names to a lot of things that might be better to have some operator, but we can't get precedence, associativity, etc. right unless we get lucky that one of them happens to be close enough. Like pipe happens to have the right properties to work for range composition. That was an accident. Fortunate, but it's a, similarly for Traversable, Monoid. One of the nice things that it's like, so like in Haskell, you can use fold map or folder, choose which are your core implementations. This allows that pretty much exactly the same way. Basically, we're trying to design APIs that are not going to age poorly. Things that we can live with, because once they go in the standard, it's like standard is where libraries go to die. It's like, so we want like loose abstractions that aren't locking us into things, and we want those abstractions to be well-founded, but we don't want it's like to like lock ourselves in too much. That's why, for example, no virtual functions. That's regex. One of the big problems with regex and ever fixing it is it's got virtual functions in. So changing any of that means that the vtable list would be different. And it's like, nothing will tell you you're using the wrong vtable. You just call the wrong function totally randomly. So it's like we want to make things smooth to upgrade. I want to work on a firm, theoretically sound foundation. I lived through threads. It's like it wasn't until Bones worked before C++ 11 that we really understood that you can't make a thread library. POSIX threads is a library. It doesn't work, cannot work, and we ignored that for decades because it worked well enough and it was useful. And it's like the compiler has to know too much about things and has to cooperate with the hardware in ways that a library just can't do. So we want our libraries to be on a firm foundation that's understood, not, oh yeah, it works, it's going to be fine. But yeah, it's like I would love to avoid the std-bind versus lambda overlap. It's like depending on when things arrive, it's like we can emphasize or de-emphasize parts of the pattern matching. We want to keep the good path obvious. It's like want to lead people to like use the things in the way that they're intended to be used and make that a natural choice. Hopefully not having to have a doctorate or postdoctorate work in category theory to understand the standard library. It's like, I certainly don't have one. Oh, yeah, one more thing. I said I wasn't going to do monads, but we can. It's like this smoothly extends to monads. I've done the work. It's like, so questions? If it's more of a comment than a question, hold it for a moment. It's like, I want to discuss this with everyone. If you want to discuss me, I'm not going to be hard to find. It's a small place. This isn't CPPCon, where even if we want to find each other, we're not going to.
So I'm kind of curious. It sounds like a lot of this comes from Pascal concepts, and if they have sort of more explicit functor support and what have you. They also have more explicit support for things like purity and things like that, which are not necessarily as present in C++. It seems like a lot of things that we've been talking about are like, you got to have your combine be associative, except for bad things happen to you. Is there like sort of a world where those kinds of things are more achievable and enforceable?
We can write concepts for a lot of these things. Right. Certainly an easy one is there is an instance. It's like the default instance of these is false. So it's like, it's an easy concept check to see if there is one. You can delay until use checking that the instance works. I haven't found a way of statically checking your implementation just because like template instantiations don't work that way. I can check an instantiation. Like, does this function look like the right shaped function? You can't quite do that for just a template instance, or I couldn't figure out a way of doing it.
We don't do definition checking because it is fundamentally impossible in C++.
It's like, I convinced myself of that, but keep hoping someone will say, oh yeah, you need this. And it's like, no, reflection doesn't help either. It's like, we just can't get at some of this machinery. Okay, yes, sorry. By definition, questions where you want information from me. Question goes up at the end. Supposed to show that first, but comments? Thank you.